I want to do a quick video walkthrough of what we're trying to do here on our mini lab with friction. We have this data table. We're looking to determine the normal force, static, and kinetic coefficients. So let's take a look. Let's take this trash can and walk through what we're going to try to do here with this activity. So you can put the box away. I'm going to grab the trash can. Now the surface, I can change the friction. So I'm just going to set the friction here. Notice you can see the surface changes. There's no friction to a lot. Depending on where you put the slider, it's going to change the mu value, right? The coefficient of friction. And now I can take my guy and I can start to push him. All right, as you can see, it shows you the forces, right? I'm applying 20 newtons to the right. It's not moving, so therefore it's matching it all the way. Now it's a lot of friction, so it's going to keep going. All right, I'm at 130. It's not moving. All right, oh, and then suddenly it jumped over. So I'm going to drop it back here, let it come to rest. And it looked like at about 130 it was going to break. All right, so let's start ticking up. So what I'm looking for is that break-even point when that thing's going to start to jump. So I'm at 140, and I'm going to keep going until it jumps. At that point, I would have reached the maximum static friction. Oh, there it was. All right, so I'm going to take it back. Try to get this up. Let's find that exact point. We'll let friction slow it down here. The speed's slowing down. I jump past it a little bit. It's a little finicky, and we'll get within a newton or so. All right, so now it stops. There's no forces. I'm going to jump ahead. 156 doesn't do it. 157 doesn't. 158. Now notice when I get to that tipping point, the moment it moves, watch what happens to the sum of the forces. Boom, right there. 159, right, we see that we now jump from no net force all the way to 41. All right, so in my data table for the trash can, I believe we know that the mass of the trash can is 100 kilograms. This maximum static, if you looked at the diagram, was 150, we'll call it 159, was right when it tipped. All right, so I'll call it 159 newtons. And now the kinetic friction is really what kind of friction we have at this point. And so now you can see that once it's moving, it doesn't matter how much I apply. That friction to the left that was static is now kinetic. And as long as we're moving, it's a fixed amount of 118. So I can apply that 118 newtons here. All right, and now I have enough information to figure out what mu must be and the normal force. So I'm going to go back in here. I'm going to flip it around, see if I can slow it down. Use a lot of force to slow this down. You can watch the speed. Now the net force is left. It's slowing down by applying a push the other way. All right, and I can kind of find some balance here. So this should balance this out. All right, let's figure out how to calculate these. So if I'm drawing a free body diagram, I have my trash can. I've got gravity down. It's not accelerating vertically, so whatever my weight is must match my normal force. And my weight is always equal to the mass times the acceleration due to gravity, which is 9.8. Which in this case is going to be 100 kilograms, the mass, times 9.8 meters per second squared, and I get 980 newtons. And if that's 980 newtons, then the normal force must also be 980 newtons the other direction. So I can write that in here. I've now calculated the normal force to be 980 newtons. And now we can calculate mu. And mu static is always equal to the maximum static friction over the normal force. And we know, because we measured it, the static friction max was 159 newtons, and the normal force was 980 newtons. And I can evaluate that. So I have 159 divided by 980, and I got 0.162. 0.162 is my mu static. And then my kinetic coefficient is just going to be my kinetic friction over the normal force. And so that value is 118 newtons over 980 newtons. All right, and so when I do that, I get 118 divided by 980, 0.12. So I get 0.12. So those are my two values. Now again, depending on where you put the sliding bar, you're going to get different values. But as long as I don't move the sliding bar This is going to be 0.162 all the way through because the surface doesn't change. We'll assume the box and the mystery box and the can are all the same surface. They're getting the same friction. So I can populate this in, and if I calculate, I should get all those values. All right, so I actually know something about my mystery box. What I do not know is the mass. And so with my mystery box, I can actually work backwards. I can determine what the normal force must be because I can measure this or that and use mu to find Fn. Right? So this box right here, the normal force is going to be the force of friction divided by whatever mu. And I can use either one to find that. And when we end up working it out, you end up getting, I think, 50 kilograms roughly is what that calculation should be. Right. And then later in the mini lab, we got an example here. I've already got a free body diagram. This is what our free body diagram should look like. You got a box. Now it's pulled along level ground, but now it's pulled at an angle. So we're going to have to find those pieces. Right. This is that angle theta that they give you. In this case, 20 degrees. This is 1,000 newtons. And we know mu because we're going to use the same mu that we calculated above. And we can work through and determine that acceleration. Once we know mu, the force of friction is simply that mu value times the normal force. Right, so once I can calculate the normal force first, I can then find what friction is, and then I can set up my sum of the forces along the surface equal to the mass times the acceleration in the x. Those forces along the surface are friction, the applied force in the x direction, that's this one right here, and that's it. Those are the only forces horizontally, and they have to equal the mass times that acceleration in the x. And in that equation, we now know friction, the applied in the x, and we know the mass of the object, and we can solve for A. So I'll leave that to you to solve, but I wanted to point out how we're going to go about doing this for this mini lab. So hopefully this gives you a little bit of direction to work through this mini lab.